So we talked about standard deviation. We talked about variance on day one, but we need to apply it a little bit now, okay? Now, in the notes that I provided for you, there's a couple things that you need to watch out for. Okay, first of all, I provided this picture for you. This comes straight from your book. We've seen pictures like this before, but what's important here is the relationship between the mean, median, and mode, depending on the type of skewness we have to the graph. So in this particular distribution, it's a symmetric graph, and notice that the mean, median, and mode pretty much line up. When we are right skewed, meaning the data tails off to the right, the mean is to the right of the mode and median, okay? When it's left skewed, meaning the data tails off to the left, the mean is to the left of the median and mode. You need to know these, okay? You need to know where the mean is in relationship to the median and mode in each of these certain shapes of distributions, okay? So make sure you have that figured out for your quiz on Tuesday. Now, the next part that we have to talk about, my guess is this is what you have. This far? Okay. So the next thing that we're talking about is the coefficient of variation. And you've heard the phrase, you're comparing apples to oranges. You can't do that. Well, you can statistically. And we have something called the coefficient of variation that allows us to compare how variable one particular variable is compared to another. Okay, how much variation exists from apples to oranges, if you will. And so what this is talking about is you're going to compare the standard deviation or the spread of lists that contain different variables, hence your apples and oranges kind of thing. And we use something called the coefficient of variation, and it's denoted this way with the lowercase c, capital V for coefficient of variation. What's important also to note is that our answer must always be expressed as a percent. So you can go through and do your calculation. You can get a decimal all you want. Your final answer needs to be in percent form. There is a sample form for this formula and a population. The idea is the same. The notation is different because, as we've talked about, the standard deviation notation for sample is different from population, as is the mean. So that we're seeing here. The coefficient of variation for a sample is the standard deviation over x bar, which is the mean. The coefficient of variation for population is lowercase sigma, which is standard deviation for population, and lowercase mu, which is mean for population. Long story short here, the coefficient of variation is the standard deviation over the mean, regardless of whether you're talking about a sample or a population. The idea, what you actually do, is the same. Standard deviation divided by mean. On your next page...
Wait, actually I do have a question.
Yes? Okay. So the next part of your notes, you have an example problem. It talks about sales of automobiles. Okay, so just take a look at that. And it says the mean number of sales of cars over a 3-month period is 87. That means over that 3-month period, they sold an average of 87 cars. The standard deviation for that situation is 5. During that same time, the mean of commissions, what's a commission?
How much you get off each sale?
How much you make off of each sale, that's correct. Okay, so the average of the commissions in that same period of time is $5,225. The standard deviation is $773. It wants us to compare the variations of these two. These are two different variables. This is what we're talking about. Here's our apples and oranges. Our apples is the number of car sales. The oranges is the amount of the commissions. While there might be some kind of relationship between those two in this particular scenario, we can compare how variable one is compared to how variable the other one is using the coefficient of variation. And so what we're going to do is we're going to set up a one for the cars. We're going to set up one for the number, I should say number of cars. Let's do that. Number of cars. We're going to look at the coefficient of that. And then we're going to look at the commissions. And we're going to look at the coefficient of variation for both of those. So scroll up a little bit, look back at that little formula, and set it up the way you should set it up, and then we'll make sure you have it right, and then we'll actually do the calculation. So do that now, please.
Wait.
Okay.
What
So
does a moo mean?
So here's what your setup should be. Okay. For the sales, number of sales of the cars, we've got the coefficient of variation is 5 over 87 because 5 is the standard deviation, 87 is the mean. For the commissions, 773 is the standard deviation, and the mean is 5,225. This should be your setup. Now go ahead and figure out the rest of it, because what form does it have to be in?
It has to be in percent.
It has to be in percent. So change those to percents and let's see what we get. What do we round to? Which place? What's the data in? What kind of tens place? Because it's always, so this is whole numbers. These are all whole numbers. So when we round, we always round to one place beyond the data. So in this place, since these numbers are all whole numbers, I have to go one decimal place more than that. So I should round to the 10th place for both. What is the percent over here? 5.7. What is the percent over here?
14.8.
Okay.
You gave us like.
Okay. So that now here's the question. It says to compare the variations. Which one is more variable? Sales or commissions? Commissions. The number's bigger. So commissions are more variable than sales. You have to answer the question. You could have also said sales are less variable than commissions. You could have gone the other way and that would have been fine. Okay? But you need to have both. Okay?
You missed it.
Now, the next part you have in your notes. Definition of Chebyshev's theorem. Okay?
Wait, that's what that's from?
This is what Chebyshev's theorem is. Okay, listen, please. Let me explain this to you. Here's where the abstractness comes in. Stop talking, please. Okay? We know, we have learned now how to find the standard deviation. But the standard deviation actually represents a unit away from the mean. Okay? So for example, if my standard deviation was 7, if I went 7 units above the mean, that would be one standard deviation above the mean. If I went 7 units to the left or less than the mean, that would be one standard deviation below the mean. Okay? And so when we talk about standard deviation, it really means a unit of measurement from the mean. And so in this particular situation in Chebyshev's theorem, when we talk about K represents the number of standard deviations, meaning the number of standard deviations, whatever that measurement is, away from the mean. And the formula here to figure this out is 1 minus 1 over K squared. And what we use Chebyshev's theorem for is to determine how much of the data is contained within a particular window based on what the standard deviation is. Now, I'm going to show you a picture here in a second that's going to make it easier to understand. The key thing here is that K, the number of standard deviations, has to be greater than 1. It cannot equal 1. It has to be greater than 1. And it doesn't necessarily have to be an integer. So what we're looking for, again, is the proportion of values from the data set that fall within that K standard deviations. Now, I want you to kind of scroll a little bit and find, because this should be the next page after Chebyshev's theorem. Okay, now I showed you just on the picture that at least 75% of all the data will be in between 2 standard deviations of the mean, meaning 2 above and 2 below. And I want to show you how the formula works so we can justify this claim. Okay? So what we're going to do is what we're saying is K equals 2. That means 2 standard deviations. There are exactly, not the value of the standard deviation, but that there are 2 standard deviations either above or below the mean. And so in the formula, it's 1 minus 1 over k squared. So in this case, k is 2. Well, what is 1 over 2 squared actually equal to? Okay, what is 1 minus 1/4?
75.
Well, think about it. Let's talk about it in fractions first. 3/4, which is 0.75 or 75%. So this just kind of proves why it's 75%. So if I go 2 standard deviations above, I go 2 standard deviations below, then at least 75% of the data will be inside that window. Okay. Again, the idea here is that whatever the value of the standard deviation is one thing. The number of standard deviations is sort of like a unit of measurement for that problem, because the standard deviation changes from problem to problem. Okay. In this case, okay, and I'm going to prove this one to you as well. And we saw it in the picture that we looked at. At least 88.9% of all the data will be in between 3 standard deviations. In other words, as I move further and further away from the mean, I include more and more of the data, right? So the closer I am to the mean, less of the data. 2 standard deviations away, at least 75%. Now if I kick it out another standard deviation on either end, Chebyshev's theorem will show us this, right? So k now would be 3, which means this number ends up being 3 squared, okay, which is 1/9. So I'm going 1 minus 1/9. That just sort of proves, since I've moved now another unit of measurement, so to speak, away from the mean, I have included more of the data in that viewing window. So again, what we're talking about here, just so we have this, okay? So you scroll back up to that. So here's an example. Okay, so let's say that we have a mean of some set of data is 65 and the standard deviation is 7.
Wait, I have a question also. What?
Now, if one standard deviation equals 7, what does 2 standard deviations equal? 14, okay? So if I went 2 standard deviations above 65, because 65 is the mean, what number puts me at 2 standard deviations above 65?
79.
How did you get that?
Because I multiplied 7 by 2 and then added it to 65.
Exactly. Okay, so you get 79. So if you weren't sure where this came from, we would just take 7 times 2, because that's 2 standard deviations, that's 14, and I add it. And so if on my, let's just put this on the picture, okay? This is what we have here, okay? What this is telling me, what this is actually telling me, is that at least 75% of the data in this particular data set, which we don't actually know what it is going to fall between 51 and 79. And again, if you wanted to, I'll come back, and that's what this says here. Picture. This is in your notes. Scroll and find that. And I want to go through this and talk about it for a second, because there's some things in here that I want you to be aware of. Okay, as we have already learned, x with the bar over it means mean. And since k has to be greater than 1, we just went ahead and talked about this situation here. Okay, this is saying, this S, as we know, stands for standard deviation. This means 2 standard deviations above the mean.
Why?
And let me show you. So it's going to be right here. That means 2 standard deviations above. So in other words, I have the mean, and I add 2 standard deviations to it, and I end up over here in this example.
What do you mean you add 2 standard?
Well, we'll find out what the standard deviation is, multiply it by 2, and add it to the mean.
Wait, why is there a red line?
Now, because I'm showing you where the window is, okay, and I'm trying to point out to you why this should make some sense. Now, this is if I go 2 standard deviations below. What I'm trying to tell you is, and you'll see this, we'll work through this in a second. You can see it up top here. What it's saying is, inside this window here, at least 75% of all the data has to be there. Okay? At least. It could be more than 75%.
How do we know that?
Because that's what Chebyshev's theorem tells us, and we're going to prove it here in a second. Okay? So that's what Chebyshev's theorem tells us is what proportion or what percentage of the data lies within that particular area. Now, let's go back to this window right here. okay? At least 75% of all the data in the set will be inside of here, okay? And then we're going to look at a couple other windows here in a second. Let me get back to this. Clear is if I extend out another standard deviation, oops. If I extend out another standard deviation, I'm including more of the data. Okay, so now I've pushed further away, and so now I've included more of the data, 88.9%, okay? So again, as we push further away from the mean, we include more of the data. If we go in closer to the mean, we include less of the data. That's what Chebyshev's theorem says. Now, in your next part of your notes, so what we're saying here is now, this is 65, 2 standard deviations above for that situation would put me at 79. That's what we're saying here. Well, so I just need to know how would I be over here? Subtract. So what would I get? 51. So this example is more concrete. 2 standard deviations above, 2 standard deviations below, and in just one second. Okay. In between these red lines, in between 51 and 79, at least 75% of the data will help you make some sense of this question. Let's see. Copy. Picture of some funky shape that's maybe right skewed. You know, it definitely, it can work for any shape. All right. But the empirical rule, here's the example that you have. So scroll down to that. Okay. Here's the situation. They surveyed some companies and found the mean amount of travel allowance for executives was 25 cents per mile. Obviously, this is an old problem. When somebody in business has to travel for their job, they get reimbursed for their mileage. In this case, it's 25 cents a mile. These days, it's much higher than that. Okay? They tell us that the standard deviation was 2 cents. What we're trying to figure out now is the minimum percentage of data values that will fall between 20 cents and 30 cents. Now, let me show you a picture and see if I can.
5. Yeah.
1 second.
No, what should
Okay, so, thank you. Okay, so here's that same picture, okay? What we're trying to figure out, see, even though this is true for 2 standard deviations, 3 standard deviations, what we're saying here is that the mean is 25 cents. Okay, we're going to go up to 30 cents and down to 20 cents. And what we're trying to figure out, and I'm just putting marks here, we're trying to figure out what is the percent in here. That's what we're trying to do. What percent of the data is going to fall between 20 cents and 30 cents, knowing that the mean is 25 cents. Okay? And so in order to do this, we have to know how many standard deviations above 25 cents and below 25 cents is 30 cents or is 20 cents. Now, fortunately, for this problem, it's easy to tell how much money is in between them. So for me, what I want to do, since the same amount of money is between 25 cents and 30 cents as is from 25 cents and 20 cents, I'm just going to focus on this one. Okay, so how far away from 25 cents is 30 cents? 5 cents. Okay, so my difference between that is 5 cents. That part we know. And that's pretty much easy to figure out. We'll have to figure out, and that's what this says. Okay, we know the difference between the mean and that upper value is 5 cents. What we need to figure out, and don't say it if you know, what we need to figure out is how many standard deviations is that? Because if we know how many standard deviations that is, then we know K. And if we know K, we can plug it into Chebyshev's theorem, and then we can find the percentage. So the question is, and I want you just to think about this, is how many standard deviations is 0.05? Think about that. Just think about it. Remember that K doesn't have to be an integer. It can be a decimal. K can be a decimal. We can have a partial standard deviation away. It just K has to be bigger than 1. That's the only restriction on it. So let's think, now that I've asked the question, let's try to think about the answer. How am I going to figure out how many standard deviations 0.05 is, what would you do?
Divide
Divide by what?
point of the standard.
By the standard deviation, which is 0.02. So what I need to do is take that difference, that 0.05, that 5 cents in between the upper value and the mean, and divide it by whatever one standard deviation is, and that's 0.02. So go ahead and do that division and tell me what you end up getting. 2.5, right? That's 2.5. Okay, so what that means is, that's 2.5. That means K equals 2.5, which here's what that means. Here's what that means. It means that 30 cents is 2.5 standard deviations above the mean, because 5 cents is 2.5 standard deviations. Now, I could have checked it the other way too. It also means that 20 cents is 2.5 standard deviations below the mean. So when you're working through your homework, you're going to have to figure out these kinds of things. What's the difference between the mean and whatever that upper value is they're talking about? And then divide it by the standard deviation. That will give you your K value. Now, once you have your K value, it's just a matter of putting it into Chebyshev's theorem. 1 minus 1 over 2.5 squared. So go ahead and do that calculation.
No.
Well, we'll turn into a percent. So yes, it's 84%. So here's what that means. And now this problem has context, so we need to write our answer in context. This is 84%. So what this means is the minimum percentage of the data between 20 cents and 30 cents is 84%. So again, let's try to talk about what that really means.
So it means
In all the situations of these companies that were surveyed, they're saying 84% of the companies reimburse their executives between 20 and 30 cents per mile. Which means at most 16% either give less than 20 cents or give more than 30 cents, because 16 and 84 is 100%. So there's a small amount of companies that actually give more or less than 30 cents or less than 20 cents, okay? That's what this is trying to say. Now, the last couple things in your notes I want to talk about, okay? So we have something called the empirical theorem, empirical rule, okay? This should be the next page. Now, Chebyshev's theorem works regardless of shape. Obviously, I showed you for a perfectly bell-shaped curve. And what we will learn is that we call that a normal distribution. We will call that a normal distribution as we move on in this course. What you have to know about a perfectly bell-shaped situation or the empirical rule is now we can talk about within one standard deviation. 68% of the data will be there. When we get to 2 standard deviations, about 95%. So that's an increase from at least 75%. And within 3 standard deviations, we have 99.7%. Now, the last 2 things on your in your notes are pictures of what bell-shaped curves might look like. Okay, here's one example. And we've talked about bell-shaped curves before because it's shaped like a bell. Kind of looks like this. Okay, and so we've got 68%, 1 standard deviation, 95%, 2 standard deviations, 99.7%, 3 standard deviations. Here's the same picture actually in the shape of a bell with the same percentages. Okay, so these are percentages you need to know. In between 1 standard deviation is 68% of the data. In between 2 is 95. In between 3 is 99.7. Let me ask you this. Let's focus on this one for a second. All right, the 68%. This is above 1 standard deviation and below 1 standard deviation. What would be this area right here then? No. What percentage is just that section? How did you get that? Yeah, so this is 34%. Well, and so what's this one over here? 34%, okay? So when you get to a problem like that, if it asks you just 1 standard deviation above, you can just take half of that one, okay? Just know that together they equal 34%. That's the empirical, or that together they equal 68%, excuse me. 34% each. That's the empirical rule. You'll need to know that for your quiz.